All right, class, let's try another one here. I got a question about 19, and let's read it together here. It says a geosynchronous satellite orbits at a distance from the Earth's center at about 6.6 Earth's radii and takes 24 hours to go around. Now, I like geosync satellites. They're kind of interesting because they go around in 24 hours. And they tell you both that. It's kind of repetitive. Geosync means that as the planet rotates, and in this case it's the Earth, which takes 24 hours to go around, this satellite takes the same amount of time to go around. And what that essentially does is it keeps the satellite over the same position. And so let's say this is one of these Stat 9 ones from DirecTV. If you put it at the equator, it's a little south of the United States, but you put it in the center. So it'd be like the tip of Texas on down to the equator. And you set it in this synchronous orbit, it's going to stay there relative to the people on the Earth. And so as we go around, it kind of appears that the satellite doesn't move. And that means I can then put up my satellite dish, I can point it at it, and then, clamp it down and tighten it up, and it's always at that same spot. And so that's why here in Southern California, when I go to put up my dish, I point it to the south because I got to go to the equator, and I point it a little to the east because it's like I said, they'll set it out there about the middle of the United States. Now, if I lived on the East Coast, if I was in Florida, I'd be pointing south again and then a little to the west. If I was in Texas, I guess I'd go directly south here. Everywhere in the United States, we'd go south because it's going to be over the center of the Earth, so it's got to be over the equator, but you would be kind of centered there. Anyways, so the geosync satellite takes 24 hours to go around. Now, so they were nice to us, and they explained what a geosync satellite was in this problem. But you hopefully got that out of the lecture, and so I thought I'd take a moment to just kind of point out a geosync satellite. And we got many of them. Most of our weather satellites are this way. They're really nice to put it, right over the Atlantic Ocean. And so it's always taking a picture of the Atlantic Ocean. And so you can see as storms develop and if they become a hurricane. And we do the same thing in the Pacific and over the central United States and all the way around the world, actually. We have excellent pictures of the weather patterns all over the world because they're all just kind of, I'll say, air quotes, parked there. Because they take 24 hours to go around. Okay, but they were also helpful in our particular problem to say that this is 6.6 times the radius of the Earth. So it's pretty far out there. If this is one radius from here to here, this is 5.6 times bigger than that one. And so it's further out than my picture seems to indicate there. So those geosync satellites are neat, but they're kind of a pain to get into orbit because they're really far out there. Our Earth is just spinning a little too fast. So you got to send it, or let me rephrase that. I guess to send it out there, we're spinning slowly, depending how you want to look at it. But we got to send it a way, way out there. All right. Anyways, so this problem says, what distance does the satellite travel in a given day? Okay. Given that it's going in a circle, I'm just going to go back to my math class and say, well, it's 2 pi r. Where r is the radius. And so 2 pi, and as the radius we said, is 6.6 times the radius of the Earth. And so it'd be 2 pi, 6.6, and now we need to look up the radius of the Earth. And I believe it's about a 6.37 million meters. Hang on, let me grab that same chart that I used on a previous problem. The Earth, 6.67 million meters, yeah. Okay, so now if I grab my calculator here, I can just go a 2 and a pi times a 6.6 times a 6.37 million meters, coming up with 2.64 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters. So 264 million meters. Okay, and so that's the first part of the question. What is the orbital velocity? Well, there's actually two ways that come to my mind on this one. And maybe I'll start with the easy one. But sadly, the easy one is almost too easy because it doesn't really have anything to do with this chapter. But I'm going to do it nonetheless. A velocity is the distance traveled, time taken. We just did the distance traveled, the 2.64 times 10 to the 8th meters. And the time is 24 hours. Now, probably want that in meters per second. So let me go ahead. If it's 24 hours, remind myself that in 1 hour there is 60 minutes and 60 seconds. And so 60 times 60 is 3,600 seconds. So that the hours would cancel. And I would be left with meters per second. So grabbing my calculator, I guess I already have the distance still in here. So I'll divide that by 24 and divide that by 3,600, and I get 3,057 meters per second. And that's really enough to answer the problem. But like I said, it really didn't have anything to do with this chapter. It just, because they gave us the information, other than it was a satellite, we took it as a circumference, and that's really from your math class. And then we went back to chapter 2 on velocity, and we had distance divided by time. But there was kind of another neat thing that was neat about this chapter that put together previous chapters. Let me point it out. This chapter, we're learning that the force between two objects is universal, Newton's universal law of gravity. And so in this case, the two objects would be the Earth and the satellite, and then the distance separating them. Okay, that's the force. But if we go back a chapter to our circular motion, which I think is one chapter back, we learned that all of that, the forces that make it turn, which in this case, when I say all of it, it's just gravity, has to equal to mv squared over r. And see, right there, that's the centripetal acceleration. So that has a velocity in it, and we could solve this problem that way. And that would, I think, be more appropriate for this chapter. But like I said, let's just confirm we get the same number here. Okay, but we also got to talk about this m, because there's two of them over here. One is the Earth and one is the object. Which one is this? And if you go back to the last chapter, you'll remember that this is the object going around. So maybe if I do this, I'll put m of the Earth and put a little e, and then m of the satellite. This is going to be the satellite. So the thing that cancels off is the mass of the satellite, which is kind of good. That means when I go to calculate the velocity, I don't need to know what the mass of the satellite is. And of course, that's how we got here. We never knew the mass of the satellite. We don't know if this is a big satellite or a small satellite. And fortunately, it really doesn't matter. And so if NASA's putting up a big one, great. If they're putting up a small one, that's fine too, because they're going to need to be going the same speed. And these R's are the same. They're probably worth mentioning. This is the distance between them, and this is the radius of the orbit, the circle, but those are essentially the same. So I can cancel those off. So on this right-hand side of the equation, all I'm left with is velocity squared. So to get velocity, I would just take the square root. And so what I have left over here is the capital G, the universal law of, or the universal gravitational constant. I still have the mass of the Earth here. And I also have the radius out. Okay. By the way, this is the common technique of getting the mass of the Earth. If you ever wondered how we know the mass of the Earth, we don't pick it up and put it on a scale. We take something that's orbiting around it, like our moon. And we do what we did here. We know the radius or the distance to the moon, so that's that term. But from the distance and the fact that it goes in roughly a circle, we can get its velocity. So we get that, we measure that, and now we can calculate the mass of the Earth. And we can do the same thing for, say, Jupiter. Jupiter, we can look at one of the many moons of Jupiter and get its speed and its distance, and from that calculate the mass of Jupiter. We can get the mass of the sun using the speed of the Earth going around and the distance around, and we can get the mass of the sun. So it's looking at these orbiting objects is how we get the mass of our planets in the first place. Now, in this case, this is kind of the reverse. We've already, looked at the moon to get its velocity and distance and get the mass of the Earth. Now we want to actually make an artificial satellite. And so we want to put up our weather satellite, let's say. And so we need the mass of the Earth to figure out how much fuel we need to put on our rocket to get there. All right, well, let's finish this calculation here and see if we can get the same number we got the simple way. And so let me put G, 6.67 times 10 to the negative 11. Let me put in the mass of the Earth, 5.98 times 10 to the 24. Again, it's in the book, and it's in my little chart here. Let me divide that by, and I guess I should put this in. This is the 6.6 times the radius of the Earth, which we said earlier was 6.37 times 10 to the 6th. So in my calculator here, I'm going to put divide by, and first I'll do the 6.6, then I'll divide that by 6.37 million, and hit enter. And now finally take the square roots of all of that. And this method gives me a number pretty close. Looks like it gave me 3,080 meters per second. And so slight difference in rounding, but that really is the third significant figure, so probably comes back to that. Anyways, hope both methods work for you. Take care.